Welcome to GDD 210 Lab 2. I'm Professor Blake and I'll be taking you through the Lab 2 example project, which covers a few camera control techniques, a 3D character controller, and raycasting. The concepts covered in this lab should provide you with the tools needed to build your own first-person game, where you can interact with objects in your scene, fire hit-scan weapons, and navigate a 3D world. We're going to start in the Lab 2.0 floating camera folder. If you open up the scene in there labeled 2.0, we'll have our first example of a floating camera controller. So here we have a little solar system to explore. You can see there's a star at the center at the world coordinates of 0, 0, 0, and we're out here on the far edge. Around the star are these floating cubes, and then there's some kind of comets with trails floating around. To explore this space, we can use the mouse to look around. Moving the mouse left to right causes our camera to pan left to right. Moving the mouse up and down moves the camera up and down. This is a free look camera, not constrained by any limitations. If we just keep moving the mouse, the camera will just keep on spinning. Now if we use the W, A, S, and D keys, we can move through our solar system. Notice how the direction the keys move us is based on the direction we're facing. So W moves us forward on the x-axis, as indicated by the red line on the bottom of the screen. You can see that when we press W, we move towards that. But when we look left or right, and then we press W, now we move forward in that direction. So it's based on the direction we're facing. It doesn't get controlled by the world coordinates. And finally, you can hold the shift key to speed up your movement, so you can fly around the scene a little faster. Alright, so this camera control system is one of the most basic you can have in a first-person game. There are no limits on which direction you can look or move. All the position and rotation changes can be applied right to the camera's transform component. So we're just moving our camera around, rotating it, changing the position. Very simple. Alright, so we're going to look at the floating camera script attached to the camera game object. So at the top of the class, we have declared two public fields, speed and sensitivity. These can be used to translate our input, our mouse movement and key presses, into the response that we want from the game. So speed's going to control how much we move when we press the WASD keys, and sensitivity is going to control the mouse sensitivity for how much we should move when the mouse moves. We're going to open up the update function. So inside of the update function, we start by declaring a sprint multiplier, and we initialize it with a value of 1. Eventually we will multiply our move speed by this value, so setting it to 1 means it won't have any effect on our speed. If we do want to apply a speed boost though, when the player presses shift, we can use the getKey function from the input class to check if the player is pressing shift. So here we have an if statement inside of it, this function which returns a true or false. If they're pressing left shift, it's true, otherwise it's false. If it's true, this block gets evaluated and we set our sprint multiplier to 4. Next, down here, we gather our movement input. Using the getAxis function, we can get a positive or negative number from the Unity Input Manager's axis called vertical and horizontal. We get those inputs, multiply them by our speed variable, our sprint multiplier, and finally by delta time, because we are applying this movement in an update function, so we want to ensure it's consistent between various frame rates. After gathering the desired front and back and left and right movement, we apply it to our transform by adding it to the current position value. We take our transform.position, we're going to add, and because it's a vector 3, what we add to it have to be vector 3's. So this is a vector 3 here, where we take our transform.forward, which is the forward vector that we're pointing in the world, and we multiply that by our forward move speed, which we've got here. And then to control the left and right movement, we add another vector 3. This one is our transform.right vector, and we multiply that by our sideways speed, which we've set up here. So we're adding how much we want to move forward and back, and then we're adding how much we want to move left and right. To rotate our camera, we first gather X and Y rotation speeds. These use the getAxis function on mouse X and mouse Y to give us the distance the mouse was moved in each direction. These values are then multiplied by our sensitivity variable and again by delta time. Notice that in this case we are using the negative value of the mouse Y movement, as the input manager is set up to return a positive value where I prefer negative, and negative where I prefer positive. You may like your mouse to work differently, so feel free to customize the controls to your liking. The way this is set up is when I push the mouse up, the camera will look up, and when I pull the mouse down, the camera will look down. If you want those to be flipped, you can get rid of the negative here. To apply the mouse input to our camera's rotation, we use the rotate function on the camera's transform component and pass in a new vector 3 with the Y speed as the X value and the X speed as the Y value. So we use our transform component, the rotate function, which takes a vector 3 Eulers as the parameter. So we declare a new vector 3, and in the Y component of the vector 3, or in the X component of the vector 3, we want the Y speed variable. And I'll show you in Unity why that is. So here's our camera, and you'll see if we rotate it this way, up and down, that's the rotation on the X-axis. You can see it changing. And if we want to rotate left to right, that's on the Y-axis. So because our up and down variable is called Y speed, we put that in the X component. Our left and right is called X speed, so we put that in the Y component. And we don't want to rotate on the Z axis at all. Alright, so using that simple script, we've created a free look first-person camera, and we can fly around in this 3D scene. So we're going to take a look in the next scene to start learning about raycasting. Inside the Lab 2.1 Raycasting and FPS folder, find the scene 2.1.1 Raycasting. Here we have two cubes moving up and down the screen. When the cubes pass each other, their lines turn green, otherwise they are red. This is accomplished by using the Raycast function inside of each of the cube's update function. A ray has an origin and a direction. In our case, the origin of each ray is the center of the cube from which it's being cast. The direction is the forward direction of the cube. So the cube on the left is facing right, and the cube on the right is facing left. A raycast is an invisible ray that starts at an origin and continues along its direction until it either hits a 3D collider or reaches a set distance to stop. The function returns a bool, so it will return true if it hits something, or false if it doesn't. Using this bool, we can plug the raycast function into an if statement, which will only execute if the raycast hits something. So I'm going to open up the script on the cube here called Raycaster. So this script is on both of the cubes in this scene. At the top of the class we have a float for speed, and then inside of the start function I'm setting the speed to a random number between 0.2 and 0.9. Inside of update, we move our cube up and down with this using the sine function inside of a vector 3. So on the y-axis we move up and down, and we're just setting the position to that value, that new vector 3. We're not too worried about this right now, we're looking at raycasting. So below that line, after we've moved, we're going to cast a ray. We start with this raycast hit variable we've called hit. So this is going to create a temporary variable which is going to store this raycast hit information. We're not initializing with anything because we don't have a raycast hit yet. So we're just starting the variable, but it currently doesn't have any value to it. Below that, we have an if statement. So this is going to evaluate this block if it's true, or this one if it's false. And inside of the parentheses, we have this physics class with the raycast function. And if I mouse over the function, you can see that it returns a bool, so we can put it inside of this if statement. It'll return true or false based on if it hits something. The first parameter it takes is an origin as a vector 3. The second parameter is the direction in which it should go. And for the third parameter, we get this out raycast hit info. You've probably never seen the out keyword inside of a function before. And what that's going to do is it's going to allow this function to set the value of this variable. So once this function gets run, it's going to cast out a ray. It's going to cast it from the cube's current position using the transform, the cube's forward direction using transform.forward to get a forward vector, and then we're passing out the raycast hit info into this variable we created up here. So if we hit something, this variable will have information about the event, the hit event that occurred. So after this function gets executed, we have a true or a false. Could also do this to make it a little more clear what's going on. We're doing this function, it's returning true or false, and we can just evaluate if it's equal to true. That actually works the same way as not having that, but it might be easier to understand what's going on if you include it. So if our raycast hits a collider, and this is true, we're going to draw a line using the debug class's draw a line function. The line's going to be drawn from our cube's position, and the second point in the line is going to be drawn to this hit dot point. So hit, remember, is this Raycast hit variable up here. And because we hit something and we passed out information about that collision, that Raycast hit, we can now use that information inside of this block, because this is what's getting evaluated if this was true. So now that we have a hit, a Raycast hit, one of the parameters of that hit is the point at which the Raycast hit a collider. That's going to be a vector 3 in world space where this hit occurred. So we're drawing the line from our position to where we hit a collider, and we're going to set the color of this line to green. If our Raycast simply didn't hit anything and went on forever, we're going to draw a red line from our cube's position to our cube's position plus our forward direction times 100. So that's going to just make that's going to be a red line. So it's going to make a line from our position just out in front of us 100 units away. So if we go back to our scene, you can see here the cube on the right is casting its ray to the left. It's not hitting the other cube because it's moved too far in front of it. So we're just drawing this red line off into the distance. If we let them come back, now you can see they've both intersected with each other. Here you can see the rays stopping on the surface of the cube that it hit. So the line coming out of the cube starts at the center. Here you can see it coming out. And the line that's coming from the other cube is stopping right on the face of this cube where it intersects with the collider. In the next scene, 2.1.2, we have a similar layout to our previous scene, but with a new cube in the center. When we run the game, you can see that the moving cubes still draw a red line when hitting nothing, a green line when hitting each other, but now a purple line when hitting the center cube. What we're doing here is using the Raycast not just to determine if we hit something, but to find out what it is we hit. Inside the spin Raycaster script on the moving cubes, we have a similar script to the last one. We declare a new Raycast variable called hit, and start an if statement with a Raycast function as the condition. So again, this function is going to return true or false, so we can plug it into an if statement to evaluate this block if it's true, and this one if it's false. So now that we know that this Raycast hit something, we want to see if we hit the spinner cube in the middle of the scene. To do so, we create a new variable with the spinner class as the type, and call it hitSpinner. We now want to set this variable equal to the spinner component on the game object that the Raycast hit. Using the hit variable, we can get the collider component of the game object that the ray hit. And from the collider component, we can call the getComponent function to get other components attached to the game object. So you can see when the Raycast hits the center cube, we're going to get a reference to the collider, that's this box collider attached to it, and then using getComponent we can get this spinner component, so we have access to this script. Now that we've called the getComponent function on our hit.collider, what we can do is check to see if the object that we hit was the center cube that has the component on it. We have another if statement here, and if our hit spinner variable equals null, it means we did not hit a component, or we did not hit a game object that has the spinner component attached to it. So if hit spinner is not equal to null, it means we did hit a game object that had a spinner component on it. So this block here means we did hit the spinner block at the center of the scene, because hit spinner is not null. If we hit something but it was not an object with the spinner component, hit spinner would be equal to null. So then we would evaluate this block. So if we did hit something that has the spinner component, we are going to do our debug.draw line with the purple line, or magenta. And that's going to go from the center of our cube to the hit dot point, just like in the previous scene. This line here is where the real power of this method of getting the thing you hit comes in, because now we have a reference to that spinner component on the center cube, and we can call this public function that's part of that class. So on the hit spinner class or component, we're calling the add spin function and passing in this power variable for how much spin it should add to the center block. If we go to this add spin function, you'll see here we're inside the spinner class, and it has a public void add spin function, which takes a float called power. So we're calling this function on the spinning cube at the middle of the scene, but we're calling it from our moving cubes that are doing the raycast. Here back in Unity we can see, if we hit play, when each cube's raycast hits the center cube, it's calling that add spin function and applying power. This left cube's power is set to 200, while the right cube's power is set to minus 400, so they each spin it a different direction. If we duplicate this spinning cube, you can see they each apply spin only to the cube they're hitting. Because of that get component function, we're getting the spinner component on the cube we're hitting with the raycast. So this is extremely powerful. This is how you can do this is what you would do for things like dealing damage to an enemy in a shooter game. You can get a reference to the enemy you hit and call a take damage function on them, for example. And then the enemy itself can handle taking damage, so if they should play like an animation, or if their health drops below 0, they can fall to the ground. So this is really powerful because you're getting the component attached to that specific game object and then calling the function on it. So now we're going to take a look at some of the other properties of the Raycast hit. If you open up 2.1.3, in this scene, the cube on the left is casting a ray in its forward direction, and it kind of rotates back and forth a little bit. When the ray hits the cube on the right, it draws a line that reflects off the surface of the face that it hit. This line is called a normal, and is a vector pointing outward from any face of a mesh. We'll get into faces and other properties of 3D mesh in the next lab, but for this you can just think of the faces as each of the 6 sides of this cube. So if we look at it here, you can see how the Raycast, the normal line comes in and hits the face, and then off of the face you get this angle, this vector that points off at the same angle as the face that you hit. So when we drag the sphere collider over, now we can see how this one gets hit. Sphere collider is made up of many faces. If we switch over to wireframe, you can see all the faces that make up the sphere. And still, the Raycast coming off is going to face outward from whatever face that it comes in at. And then we can move the Capsule Collider and look at how that is affected. So on our Capsule Collider, because we're hitting this on an angle, the Capsule Collider is kind of angled this way. You can see that the normal comes out up on the y-axis here. And again, that's because that is the... a little tough to see here. But that is where the faces that make up the Capsule Collider are pointing out that direction. So the normal is just a vector pointing outward from a face on a mesh. So we're going to take a look at how you can get that and then why this is important. If we open up the normal Raycaster script, so here we're just moving and rotating our cube. Here's our Raycast hit variable like we've been doing. Again, we have an if statement to make sure that we're actually hitting something with our Raycast. So if we hit something, and then like in our last example, we want to find that spinner component which all of those shapes had. So if we hit the spinner component, we know that we have hit one of these cubes, the sphere or the capsule. So what we do is we draw a magenta line from our Raycasting cube's position to where we hit it, hit dot point. Then we draw another line from our hit dot point, so where on the surface the Raycast hit. And then we draw it to the hit dot point plus the hit dot normal. So the normal is a vector 3. It's a vector that points outward from the surface of the mesh, so we can add that to the point that the ray hit, and we get the result like we saw. Alright, so normals are important for the character controller that we're going to look at in the next scene. They can be used to tell if a player is standing on a flat surface or a steep slope, and we can use that to determine if the player should be moving like slowly, walking up a hill, or quickly, walking down a hill, or if it's a slope that's too steep, it should act like a wall. So I'm going to open up the next scene normal example. And here we have a kind of a planet with a bunch of these characters positioned all around it. You can see they're all just kind of at random angles, all just above the surface of this planet. When I hit play, I'm going to immediately pause it. You'll see instantly they all snap to face as if they were going to stand upright on the surface. And then as we let them fall to the ground, they're all standing upright on this little planet. And they just run around. You can see as they go up these little bumps, they again orient themselves as if they were walking upright on it. So this is done using normals. I'm going to open up one of these player scripts, normal player example. And in here you can see we have a reference to the rigid body that is attached to the little character. And then we have a vector 3 for the move direction that we want to move the character. Now in the fixed update function, we are adding a movement force to the rigid body. This is kind of just a random movement to make them run around the planet. And then we're also adding this force that simulates gravity on this like small planet. Because the planet's at 0, 0, 0. If we just add a force opposite the position of the character, it acts like gravity and pulls it inwards towards the center of the planet. That stuff isn't as important here, but what we do want to look at is how this normal works. So as usual, we have a Raycast hit variable called hit. We do our Raycast from the character's position, and then we cast it inward towards the center of the planet. Kind of the same thing we did here. We're just putting minus our position, so that no matter which side of the planet we're on, it's going to cast the ray towards the center of the planet because it's at 0, 0, 0. And then out hit fills in this hit variable with the Raycast hit info. And if we did hit something, we just take our rigid body transform.up, I'm sorry, not the rigid body, but the transform components up value, and we set it equal to the hit.normal. So remember, the normal is a vector pointing outward from the surface that we hit with the Raycast. So if one of these characters is casting a ray downward towards the planet, so the rays are going to be cast from the center of the player down, and you can see that gives the hits the surface of the planet, and then the normal that comes up off that surface gives us a vector which we can align the player with so that it's always walking upright. So that's an example of when you could use normals, and then again we're going to get into them more with the character controller we're going to look at, but they can be used to determine if the player should be able to walk up a slope or not. If it's too steep, it can stop them. Can be used to add or subtract speed from their movement for going up or downhill, things like that. Alright, now that we've looked at some of the ways to use Raycasts, let's combine our camera control lesson with the Raycast lesson. I'm going to open up 2.1.5 FPS. So here we have a first-person camera controller that works similarly to the free look camera from the first scene. In this case, there are some minor changes. The first important difference to note is the camera is actually a child of the parent player game object. If you look in the hierarchy, we have a player game object, and then as a child of that, the camera is inside of it. What this lets us do is rotate the player left and right when we turn the mouse left and right, but only the camera, and in this case the player's arms, go up and down when we look up and down. Because we don't want the player to tilt up and down like this when they look up and down. We just want the camera to go up and down. And you can see if we click, we cast out a ray. It tells us when we hit things in the console. You can see I hit the ground, hit target 1, target 2, target 3, or the block underneath me. Inside the player Fps Controller Script, we have a public float at the top for our mouse sensitivity, and then we have a public transform for a reference to the camera's transform. Remember, the camera is a child game object of the player. So if we want to just turn the camera, we need a reference to its transform versus manipulating the player's transform. Next we have a float for cam rotation. We're going to initialize it at 0, but I'll get into this in a second. And inside start, we use this cursor.lock state to lock the cursor to the screen, and that just prevents the mouse from moving outside of the game window while you're playing, unless you hit escape to regain control of the cursor. Alright, inside of update, we first start with getting the mouse Y input. So that's going to be moving the mouse up and down. We set a float mouse Y input equal to the get axis mouse Y function, and we multiply that by the mouse sensitivity that we set above. Next, what we're going to do is use the cam rotation float so that we can lock the mouse movement. When the player looks up and down, we don't want them to look past 90 degrees in either direction. Otherwise, they could just loop in circles. So what we do is we subtract our mouse input Y from our cam rotation. So remember, cam rotation starts out at 0, and then we're going to subtract this mouse input. We're subtracting it because, if you remember in the other game, the space scene, I was using negative input on the y-axis. This is kind of the same reason, so that when you move the mouse up, the player looks up, and when you move the mouse down, the player looks down. So we're subtracting from cam rotation our mouse input, and then we're going to lock our cam rotation between -90 and +90. So we set cam rotation equals, the mathf class has a bunch of functions you can use on floats. So clamp is a function which takes in a value, and then it clamps it between the minimum and maximum values that you set for the second and third parameter. So the value that we want to clamp is cam rotation, and then the minimum is -90 and the maximum is +90. So if we're already at -90 and then we try to subtract another 1, this function's going to say that's too far, clamp it to -90, and the same goes for the other direction. And this just prevents the player from looking underneath himself too far or looping his head over the top. So now we have in cam rotation the value we want to set our rotation to, that clamped rotation. So on our cam transform component, that's the transform on the camera, we're going to set the local rotation because we want this camera to maintain its rotation with the player. So if the player looks left, we don't want to override that the player is looking left. We just want to override the up and down rotation. So we can set the local rotation, which is a quaternion, to a new value. We're going to use the quaternion class with the Euler function, which will convert a vector 3 into an Euler, or into a quaternion. Inside of the Euler function, we have to pass in a vector 3, so we create a new vector 3. And in the x component of the vector 3, we're going to put our cam rotation, and then 0, 0 for the y and z. And you can see in here why we do the x component. If we put our pivot on the local space and then rotate on the x-axis, you can see that's the one that looks up and down. So that's the one that when we pass in that vector 3, we want to rotate the x-axis. Alright, so now we have we've updated the local rotation of our camera transform, so that handles all of our input on the y-axis, clamping the rotation, and then setting the rotation of the camera. Next, we just need to rotate the player left and right for the mouse X input. In this line, we are creating a new float for mouse input X, setting it to the getAxis function for mouse X, multiplying that by mouse sensitivity. On the next line, we're setting the player's transform.rotation. So this is the parent player object. And again, we're using the quaternion.Euler function. And here what we want to do is take our current rotation, our current Euler angles, so that's a vector 3 representation of our rotation. Remember that a rotation is a quaternion, but you can use transform.Euler angles to get a vector 3 representation of that quaternion. So what we can do there is take our current Euler angles, our current rotation, and add to it a new vector 3. And here we're just putting in the mouse input X into the y component of the vector 3, because again, when we rotate the player left and right, that's their y-axis. You can see rotating in the inspector. So with the camera, we're moving up on the x-axis to look up and down, and then the player transform is rotating on the y-axis to look left and right. So now we've handled the mouse Y input up and down and the mouse X input left and right. And after that we are doing our raycasting. So first we have this conditional check. If the input mouse button down 0, that's if the left mouse is clicked. we create our Raycast hit variable. We cast a ray from the camera transform dot position because we want the ray to come out from the camera. And we set the direction to the camera transform dot forward. So it's always going to go the direction the camera's looking. Then we pass out our Raycast hit information into our hit variable. So that's inside the if statement. So if we hit something with our Raycast, as usual, we draw a line. Here I'm drawing it from the camera's position, and then I'm just drawing it down 1 unit because it's a little hard to see if it comes out right from like the player's eye. So this way it comes out just below us, and then it goes to the hit dot point again. So whatever we hit with the Raycast, we're going to draw the line to there. We're going to make it green, and then you can add in how long you want to draw the line. So I put 1F there to draw it for 1 second. We also want to see what we hit with our Raycast, so we do debug.log, which takes a string. We use the hit to get the collider component that we hit. We get the game object that that collider is on, and that game object has a string for its name. So this name is going to be whatever it is named here in the hierarchy. Ground, block, target 1, target 2, target 3. And as always, if we didn't hit anything with our Raycast, we're just going to draw a red line out in front of us. Again, going from the camera position down 1 unit, and then the camera's forward times 100 just to send it really far out into space. In the scene in 2.2, first person movement, we start building our character controller. This is a system that controls the player's movement without relying on the rigid body component to move around. A character controller script moves the player around by manipulating its transform, but it performs collision checks with raycasts against colliders. It may feel like a physics object, but that's because it's a well-designed character controller that provides tight controls and predictable experience. So we're moving around in this scene, colliding with walls. You can see I can go up this slope here. This one is too steep, so I can't walk up it. I can walk down it, or I could jump up it. You can also handle jumping up and down. Alright, so let's take a look at our player's FPS Movement Script. You can see we have also the character controller component on this player. This is a Unity component. You can just type it in here and add it. And this works kind of like a rigid body, how you would add velocity to your rigid body. But in this case, whenever you want to move, you tell your character controller component where you want to move to, and it will handle all of the collision checking. You can see it also draws a capsule collider around your shape. There is no rigid body on the player, and there is no other colliders. So this is just drawn from the character controller component. You can see here we can change how wide we want the collider to be, how tall, and you can set the slope limits for how steep of an angle the player can walk up. Or if they are walking up a set of steps, you can set how wide they can handle steps to walk up them. So we also have attached to this the Fps Controller Script. That's the one we just built in the last scene to look around. So that's just been added on to handle our looking around, but we don't really need to look at that for movement. In our movement, we only want to handle passing in information to the character controller. So this looking around script is going to work for us without having any effect on our movement, which is pretty nice. So I'm going to open up the Fps Movement Script. Alright, so in here, the first thing we need is a reference to that character controller component. We've just called it CC. Next we have a float for move speed, gravity, and jump speed. So these are how fast the player is going to move when he is moving. The gravity will bring us back down to the ground. Jump speed, when we hit spacebar, how fast to move the character up in the air. There's also a float vertical speed. This is just to hold our vertical speed as a variable. Because we don't have a rigid body, there's no automatic velocity math or anything. So when we want to jump, we're just going to add jump speed to our vertical speed. And then we're also going to we're going to subtract our vertical speed by gravity to bring us back down. So this is going to handle where we are above the ground, basically. So inside of update, now remember this is not a rigid body, so we can update it inside of update. First we're going to create a new vector 3 called movement and set it to 0. And this is the movement that we want to send into our character controller for this update frame. So at the top of the frame we're going to set it to 0 because we haven't, if we don't press anything, we don't need to pass any information into the character controller, so setting it to 0 is fine. Next we want to handle the movement on the X and Z axis. This is left, right, forward, back. The y-axis will be up and down, which we'll handle later on. But for right now, we're creating a float forward movement. We're going to set that equal to the vertical getAxis function, so that's W and S, or up and down arrows. We're going to multiply that by our move speed, and then delta time. Our side-to-side movement, the A and D keys are left and right arrows. We're going to set to the getAxis horizontal, multiply it by move speed and delta time. So now we have our movement input that we want. And we're going to add those to our movement vector 3. So we take our movement plus equals to add to it. And first we're going to add this vector 3. So this is our forward movement. And we want to add that in the direction we're facing. So we can do our transform.forward. So whichever way we're facing, we're going to move forward in that direction times our forward movement variable. And remember, this lets us, even if we turn 90 degrees to the left, our transform.forward is now facing that direction. So we can just move in that direction to go forward. Next, we add another vector 3, transform.right, and we multiply that by our side movement variable. So we've taken this vector 3, we've added this vector 3 to do our forward movement, and then we've added this vector 3 to handle the left and right movement. So our movement variable now has it's now a vector that represents where we want to move. We've pressed, say, W and D, so we want to move forward and to the right. So we've added that forward here and that right here. Next we want to add our vertical input to movement on our Y component. First we want to see if the player needs to jump. So if the character controller .isGrounded property, this comes from the character controller, it'll tell us if the player is on the ground or not. So we can just check that as a bool. Remember, putting that in the parentheses is the same as doing equals true. So if this is true, we're going to set our vertical speed to 0. If we're on the ground, our vertical speed should be nothing. And then, because we're on the ground, we can check for jumping. So we're going to do another if statement, if input.getKeyDown space. So if the player's pressed the space bar, and we're on the ground because we're inside here, we're going to set our vertical speed equal to our jump speed variable. So now that we've handled our vertical speed, either setting it to 0 on the ground or setting it to jump speed if we want to jump, we can now add gravity to our vertical speed. So we take vertical speed plus equals gravity times time.delta time. So every frame we're going to be adding our gravity to our vertical speed. Then we can plug that vertical speed into our movement variable. We'll say movement plus equals, and then we make this vector 3 from our player's transform dot up. That gives us a vector 3 on the y-axis. We multiply that by our vertical speed, which we've updated all in here. And then we multiply all that by delta time. So now we've gone through and we've set all of the components of the vector 3 movement variable. So we have our forward, back, left, and right movement, our up and down movement on the y-axis. Now all we do is we tell our character controller to use the move function that's part of the character controller script, and we pass in our movement variable. And now the character controller is going to handle all the movement. We don't have to do any checks for collisions with walls or anything like that. The character controller is going to do that for us and move the player appropriately. So even if we pass in that we want to move forward one space, but if there is a slope there, like in our scene, if we want to move forward one, we're not telling it to go up the hill or anything, we're just saying move forward one. The character controller is going to notice that there's a slanted ground here, and it's going to move us up the slope as we would expect it to. So that is a nice, simple character controller you can use. You don't have to mess around with rigid bodies and physics at all. You get nice, predictable behavior. And it's a good start for a first-person game. The 2.3 Raycasting scene is an example of combining the player movement with Raycasting. In this example, you can press the 1, 2, or 3 keys to execute different types of raycasts. So 1 is the normal raycast that we've been using. It prints out the name of the game object that it collides with. If you press 2, we use a raycast all function. And this is a raycast that will not stop when it hits the first collider that it hits, but it will keep going. And it will return all of the colliders that it intersects with. So if I go to this corner over here and press 2, you can see a green line came out from the player. And if I look at the console, it says Raycast all hit 0 tall block. So in that case, I only hit this tall block. If I aim a little bit lower and press 2, you can see I hit 0 the short block, and then hit 1 was the tall block. So it's giving me the order in which it hit things starting at 0. So the ray came out from the player, it hit the short block, and then hit the tall block. If I aim down, I should be able to hit. So here I hit the short block, the ground, and the tall block. So using Raycast All can be useful if you want to see everything that you would have hit in front of you. And then the 3 key, if I click these orbs here, they're called health orbs in the hierarchy. So they have this health script on them with how much healing they should do, just as an example of how you could make like a health kit in your game. So if I press 3 on it, you'll see it disappears, and in the console it says hit health orb has 25 healing. And then the health orb prints out enjoy. So we're able to see how much healing the health orb had, and the health orb will actually print out a message in the console. So we're going to open up the player and look at these different raycasts. At the top of this class, we have some of the same things: the mouse sensitivity, and the camera transform, the cam rotation, setting the lock state in the start function. This is all the same as the previous FPS controller. So we get our mouse Y, mouse X, and we set the rotations. Then down here is where we do the different raycasts. So if you press the 1 key, we call this simple raycast function. And in here we create our raycast hit variable hit. Cast out a ray like we've been doing. Draw a line to the hit point, hit position. And then we print out the name of the game object that we hit. We've seen that one a few times now, so I'm not going to spend too much time on it here. Back into our update function, if you press the 2 key, we do this Raycast All function, which is right here. So Raycast All, instead of a bool like the Raycast function, the Raycast All function returns an array of Raycast hits. So what we can do is, instead of Raycast hit like we have been doing, we do Raycast hit array hits. So this is going to hold all of the Raycast hits that come back from the Raycast All function. Because this function returns an array of Raycast hits, we can just do this all in one line. Raycast hit array hits equals physics.raycastall, and the Raycast All function takes an origin and a direction. Because it returns an array of Raycast hits, we don't need to pass out any kind of hit info like we were before, because this is going to return all of that Raycast hit information, and we're setting it to this variable here. Now, because we don't have a bool for if we hit something or not, we can do instead if hits.length is greater than 0. Because we're creating this array here, an array has a number of items inside of it. If we don't hit anything, the length of this array is going to be 0. If we do hit something, the length will be greater than 0. So this if statement here lets us know if we hit something. If we did hit something, we want to create a for loop and go through everything that we hit, and then do this draw line and debug log for each item that we hit. So to do that, we create a for loop. We create a integer I that we set to 0. We want to loop through this for loop while I is less than hits.length. So what that means is I starts out at 0. We want to keep going through this loop until while I is less than hits.length. So if we hit 2 items, the length of hits is 2. So this will loop twice. And then the I++ adds to the value I here. I don't know how much you've gone through arrays yet, but for now you could just copy this one. It's pretty simple way to iterate through all of the items in an array. And what that's going to do is give us the ability to get the item in our hits array at the index I. So the very first Raycast hit in the array will be at hits 0, and because we start at I equals 0, we can draw our line from our camera transform.position, and then we offset it a little bit, and the point we're going to draw it to is the hits.I dot point. So we're going to get whatever Raycast hit is at hits I in the array, and we're going to get the vector 3 point inside of that. Then we'd make it green and we draw it for 5 seconds. After that we do debug.log. We print out Raycast all hit, and then we print out the index that we're currently looking at, this value for I. So that's why when you saw it before, it started at 0, then went 1, 2. That's just us looping through this array and adding to I each time we loop through it. Then we print out hits I.collider.gameObject.name. So again, we're getting the name in the hierarchy of the game object. Finally, if you press the 3 key, this is back in update, we're going to do this pickup health function. And this works similarly to the one we saw in an earlier scene. We create a Raycast hit variable. This is back to the normal Raycast function, so it returns a bool, true or false. If we hit something, we want to draw a line to the thing we hit. We've done that a few times now. And here's where we are looking to see if the thing we hit is a health orb. So we create a new variable. The type is health orb, and we name it hit orb. We set that equal to the hit.collider.gameObject.getComponent health orb. So remember, if the game object has a health orb component attached to it, this will become a reference to that component. If it does not have that component attached to it, this will be null. If it's not null, meaning we hit a game object with the component attached, we can say debug.log hit a health orb has, and then from the reference to the health orb component, we can get this public float healing value. You can see in the health orb script it has the public float healing value. Because it's public, we can access it when we have a reference to the script or to the component. So we print out has, we get this float number for the healing value plus healing. So it's just going to tell us how much healing power that health orb has. And then we get our reference to the hit orb again, and we call this onUse function, which we can go check out in the health orb class, the public function onUse. And you can see when we use the health orb, it just has the health orb print out health orb plus heal message, which is a variable we've set up here. Heal message equals enjoy. And then it destroys the game object that this component is attached to. So it removes it from the scene after you use it. So those are our different ways of using raycasting combined with the player movement. Finally, in the 2.4 FPS in physics scene, again we have our first-person controller. We can walk around, and in this scene we have some examples of how to interact with physics objects from our player. So here I'm pushing this cylinder around. I can push this box over or pull it towards me using left and right mouse buttons. And same with these. So these are all physics objects, and I'm just raycasting to them to add a force to them. So I'm going to go into the player physics script attached to this game object. Most of the same stuff here. We have mouse sensitivity, camera transform, camera controller, and then this new variable strength. That's how much force I should apply when I click on a physics object. Cam rotation, we've seen. Setting the lock state and start, we've seen that. Inside of update, we are just getting the aiming up and down, left and right. We've already seen that. Here in fixed update, because we're working with physics objects, we only want to apply forces to them in fixed update. So if you are pressing the left mouse button, we call this push function, which takes a float for the direction you want to push it. So we put 1 for pushing, and if you want to pull it, we do -1. And that's when you press the left or the right mouse button. So this push function should look pretty familiar. We create a Raycast hit variable called hit. We do our Raycast inside of the if statement. If we hit something, we draw a line to it. We've done that a few times. Then we look for a rigid body attached to the collider. So if we create a rigid body variable called hitRB, and its type is a rigid body, again we use the hit.collider.getComponent, and this time we're looking for a rigid body, so that's what we put in there. If the collider that we hit has a rigid body attached to it, this becomes a reference to that rigid body. And if our hit RB is not null, meaning we hit something with a rigid body, we can use that hit RB, which is a rigid body component, and call a function on it, add force at position. So this lets us add a force to a rigid body from a position. The force we want to add is the forward vector of our camera transform. So whatever direction we're looking is the direction we want to add the force. We multiply that by the strength that we set up here. Multiply that by the direction so that we can push and pull. So if this is positive, we'll push it forward. If it's negative, it'll push it backwards or pull it. And then the position at which we want to add the force on the rigid body, we can use hit.point. So when we click on a cube, for example, if we click the top right corner here, it's adding the force to that corner, so you're going to get a little bit of rotation to it. If you add the force to the center of the cylinder, it accelerates it kind of slowly, where at the outside you can spin it a little quicker. Alright, so that wraps up our last example of using raycasts. There's a lot to unpack in here. I just wanted to provide a lot of examples of how to use these. This is the core concepts used in making like an FPS game or a third-person game. You have your character controller, handles your player movement. It's going to be a lot more responsive than trying to roll your own physics control where you have a rigid body and you're adding forces and changing velocities and things. And it also gives you a lot of raycasting you can use, and this gives you a lot of interaction with things in your scenes. You can get references to components on any game object that has a collider. So go ahead and use what you've learned in this to make your own game for this lab, and I look forward to seeing what everyone creates.